Welcome to the deep dive. Today we're going to be exploring, this incredible scientific endeavor, the Large Hadron Collider, the LHC.
The LHC is fascinating. I mean, it's a global project, it's pushing the boundaries of really what we know about the universe.
Yeah, so picture this, right? Like a 17-mile-long tunnel
Wow.
beneath the France-Switzerland border. And it's housing the world's largest and most powerful particle accelerator.
That's incredible.
It is. And we're talking a behemoth of a machine here, requiring the expertise of over 10,000 scientists.
Wow.
From over 100 countries.
It's a huge collaboration.
It is a huge collaboration.
Yeah.
And get this, when it's running, it draws a third of the power of the entire city of Geneva.
That's a big power bill.
Talk about a power bill. So we're going to be sifting through excerpts from various articles on the LHC and its detectors. And I can already tell you, it's mind-boggling stuff. Before we get ahead of ourselves, what exactly is the LHC trying to achieve?
The LHC, it's designed to answer some of the most fundamental questions about the universe. What is it made of? How did it all begin? What are the forces that govern everything we see and even don't see?
So it's like a cosmic detective story, and the LHC is our magnifying glass.
That's a great analogy. By smashing these particles together at these incredibly high energies, we can create conditions similar to those that existed just fractions of a second after the Big Bang.
Wow.
So it's like recreating the universe's baby pictures.
So we're looking at the universe's baby pictures, and by studying the wreckage, the debris from these collisions, we can piece together clues about its origins and the fundamental laws that govern it.
Precisely. So the LHC is a particle accelerator. But it's not just any particle accelerator. It's specifically designed to smash hadrons.
Okay.
And these are composite particles that are made up of even smaller particles called quarks.
Okay, so like protons and neutrons, the building blocks of atoms.
Yes. Protons and neutrons are both hadrons. And smashing these particles together at nearly the speed of light releases an incredible amount of energy.
Wow.
And it's this energy that allows us to create and study particles that, don't exist in everyday life. And these particles might hold the key to understanding the universe's greatest mysteries.
Okay, now I'm really intrigued. So what are some of these mysteries that physicists are hoping to solve with the LHC?
Well, one of the biggest mysteries is the Higgs boson. It was discovered in 2012, but there's still a lot we don't know about this particle.
Okay.
And it's crucial to the standard model of particle physics, because it's what gives other particles their mass.
So without the Higgs boson, would everything just be massless? Like cosmic ghosts just floating around?
That's a simplification, but you're getting the idea. So the Higgs field, it permeates the entire universe, and particles, they interact with this field to acquire mass. And the stronger the interaction, the heavier the particle. Without the Higgs, the universe would be a very different place. Stars, planets, even you and I wouldn't exist.
Yeah.
So it's pretty important.
It's a lot riding on one particle.
No.
It sounds like we need to learn as much as we can about the Higgs. What else is on the LHC's target list?
Another exciting area is supersymmetry, or SY for short. This theory, it predicts that every known particle has a partner particle, a heavier supersymmetric twin.
Okay, so like a mirror universe of particles.
Yeah.
It's almost too crazy to imagine. But if it's true, what would that mean for our understanding of the universe?
It would be a revolution in physics. Supersymmetry could help us to unify the fundamental forces of nature, and it could even provide clues about dark matter.
Okay.
And that makes up, a large portion of the universe.
Yeah, dark matter is another big mystery, isn't it?
Yeah.
We can see its gravitational effects, but we haven't actually been able to detect it directly.
Right. It's like knowing the wind is blowing, but not being able to see the air. So dark matter, it doesn't interact with light, so it's invisible to our telescopes.
Okay.
We know it's out there, though. And the LHC, it might just be powerful enough to produce dark matter particles in the debris of its collisions.
No, we've got the Higgs boson, supersymmetry, dark matter.
Yeah.
Any other cosmic enigmas on the agenda?
There's also the possibility of extra dimensions. String theory, it's a theoretical framework in physics, and it suggests that there might be more than the 3 spatial dimensions that we experience every day.
Okay, my brain is starting to hurt just think about that. More than 3 dimensions.
It's mind-bending, isn't it? These extra dimensions, if they exist, they're curled up, hidden from our perception. But the LHC, it might be able to detect their influence by looking for tiny discrepancies in the way particles behave.
So like the LHC is searching for subtle fingerprints left behind by these hidden dimensions. What else?
Then there's the question of antimatter. Why is there so much more matter than antimatter in the universe? Every particle has an antiparticle, with the opposite charge, and when they meet, they annihilate each other, releasing a burst of energy.
So if matter and antimatter were created in equal amounts at the beginning of the universe, why didn't they just cancel each other out? That's quite a puzzle.
Exactly. This asymmetry between matter and antimatter, it's one of the biggest unsolved mysteries in physics. The LHC, it might be able to help us understand this imbalance by studying the subtle differences in the way matter and antimatter particles behave.
It seems like the LHC is tackling some of the biggest questions humanity has ever pondered.
That's what makes it so exciting. The LHC, it's truly a marvel of engineering and scientific collaboration. It really has the potential to revolutionize our understanding of the universe and our place in it.
Okay, so I'm ready to get into the nitty-gritty of how the LHC actually works. It's not just one giant machine, right?
Yeah.
There are different experiments happening at the LHC.
You're right. The LHC is, well, it's like a giant circular track with several pit stops. And at each pit stop, there's a massive detector. Each one is designed to study, different things.
So it's like a multi-pronged approach using different tools to investigate different aspects of particle physics.
Exactly. For this deep dive, we'll be focusing on two of the main experiments, ATLAS and CMS. And these are, well, they're the largest general-purpose detectors at the LHC. They're capable of observing a wide range of phenomena.
ATLAS and CMS, I feel like I've heard those names before. They sound pretty impressive. What makes them stand out?
Well, they're massive, absolutely massive, and incredibly complex. They're designed to track and identify the thousands of particles that are created in each proton-proton collision.
It must be like trying to piece together a puzzle with thousands of pieces all moving at nearly the speed of light.
It's a monumental task. But that's where the ingenuity of, these LHC scientists and engineers comes in. These detectors are marvels of engineering, using cutting-edge technology to capture and analyze the fleeting traces of these subatomic particles.
Okay, I'm eager to learn more about ATLAS and CMS. But before we do, can you tell us a little about the other experiments at the LHC? You mentioned there were several pit stops along the way.
Right. In addition to ATLS and CMS, there are several specialized detectors, each designed to address specific questions. For example, ALICE. It focuses on studying quark-gluon plasma, and that's, well, it's a state of matter that existed in the very early universe.
Quark-gluon plasma. That sounds like something straight out of Star Trek.
It's pretty amazing stuff. Think of it as the primordial soup that existed just moments after the Big Bang. So superheated, incredibly dense state of matter where quarks and gluons, the fundamental building blocks of protons and neutrons, roamed freely.
So by recreating this quark-gluon plasma at the LHC, scientists can study the conditions that existed in the universe's infancy.
Exactly. It's like having a time machine, allowing us to look back billions of years to the universe's birth. And then there's LHCb. And this detector, it's specifically designed to investigate the differences between matter and antimatter.
Okay. So this is the one trying to solve that matter-antimatter asymmetry we talked about earlier.
Yes. LHCb, it's looking for tiny discrepancies in the way matter and antimatter particles behave. These differences, however small, they could hold the key to understanding why our universe is dominated by matter.
It sounds like each of these detectors is, it's like a specialized detective, bringing its own unique skills and tools to the investigation. But before we delve deeper into the specifics of ATLS and CMS, I'm curious about the data itself. We're talking about smashing particles at nearly the speed of light. That must generate a tremendous amount of information. How do scientists even begin to make sense of it all?
You're absolutely right. The LHC produces an unbelievable amount of data. We're talking 1 petabyte of raw data per second.
A petabyte per second. I can't even wrap my head around that number. It's like downloading the entire Library of Congress every second.
It's mind-boggling, right? But the LHC scientists, they've developed incredibly sophisticated systems to manage and analyze this data deluge. And they use a multi-tiered system. It starts with a trigger that filters out the most interesting collisions in real time.
Okay, so it's like having a super fast librarian who can scan millions of books per second and pick out the ones that might contain the secret code.
Exactly. The trigger system discards the vast majority of the data, keeping only the events that have the potential to reveal new physics. And even after this initial filtering, there's still an enormous amount of data to process, and that's where the worldwide LHC computing grid comes in.
The worldwide LHC computing grid. That sounds pretty impressive.
It is. It's a global network of computers that share the load processing and analyzing the data from the LHC. This distributed computing system, it allows scientists all over the world to, collaborate and contribute to the analysis.
It's like having a giant interconnected brain. with each computer representing a single neuron, all working together to unravel the mysteries of the universe.
That's a great way to put it. The LHC is not just a marvel of engineering and physics, but also a testament to the power of global scientific collaboration.
Okay, I'm trying to get a sense of the scale and the complexity of this operation. We've talked about the LHC's goals, the different experiments, and the data challenge. Now I'm ready to dive deeper into the heart of the matter. Let's start with ATLS and CMS, those all-star detectives you mentioned earlier. What makes them so special?
Both ATLS and CMS, they're general-purpose detectors. So that means they're designed to look for a wide range of phenomena, from the Higgs boson to supersymmetric particles and even signs of extra dimensions. They're like the Swiss Army knives of particle physics, capable of tackling a variety of tasks.
Sounds like they have their work cut out for them.
Yeah.
How are they designed to handle this cosmic detective work?
Well, think of them as giant, multi-layered onions. Each layer plays a crucial role in detecting and identifying the particles created in the collisions.
So it's not just one giant camera taking a snapshot of the collision. It's a series of specialized instruments, each with its own task, working together to reconstruct the event.
Exactly. The innermost layer is the tracker, and that uses silicon sensors to precisely map the paths of charged particles as they, fly away from the collision point.
So it's like a microscopic detective dusting for fingerprints, but at a subatomic level.
A perfect analogy. So the tracker, it allows us to see the trajectories of these particles, which gives us clues about their momentum, their charge, and other properties.
And what happens as these particles move outward through the detector? What other layers are waiting to greet them?
Next up are the calorimeters, and these are designed to absorb the energy of the particles and measure it. There are two types: electromagnetic calorimeters for particles like electrons and photons, and hadronic calorimeters for heavier particles like protons and neutrons.
So it's like a cosmic obstacle course for these particles, with each layer revealing more information about their identity and behavior.
Precisely. By measuring the energy deposited in each layer, we can reconstruct the energy of the original particle and get a better understanding of what happened in the collision.
I'm guessing these calorimeters are pretty massive to handle the energy of these collisions.
You're not wrong. For example, ATLAS calorimeter, it uses liquid argon, which has to be kept incredibly cold at -184 degrees Celsius to function properly.
That's colder than the surface of Saturn. I'm sensing a theme here. To understand the universe's hottest moments, we need some of the coldest technology.
It's true. The extremes of science often go hand in hand. And speaking of extremes, let's not forget about muons. These are they're special particles that can pass through meters of material without interacting much. So they have their own dedicated detectors, usually in the outermost layer.
Muons, they sound like the Houdinis of the particle world escaping from the inner layers of the detector.
They are. And by studying their paths, which are less affected by the material of the detector, we can learn even more about the original collision and the particles that were created.
Okay, so we have the tracker, the calorimeters, and the muon detectors all working together to paint this picture of these high-energy collisions. But with all this data being generated, how do scientists even begin to sift through it all? It must be like looking for a needle in a haystack, but the haystack is the size of a planet.
You're right. It's a monumental task. And that's where the trigger system comes in. It's like having a team of super fast librarians who can scan millions of books per second and pick out the ones that might contain the secret code.
So the trigger is looking for specific patterns, specific events that stand out from the background noise.
Exactly. Think of it this way. If you were looking for a specific grain of sand on a beach, you wouldn't examine every single grain, would you?
No, that would take forever. You'd need some way to narrow down the search.
Exactly, and that's what the trigger does. It acts as a super fast filter, analyzing each collision in real time and selecting only the most interesting events for further analysis.
So the trigger helps to narrow down the search, focusing on the most promising events, those that might hold the key to new discoveries.
Precisely. And even after the trigger, there's still a huge amount of data to analyze. That's where the worldwide LHC computing grid comes in, that global network of computers we talked about earlier. It's a remarkable system that allows thousands of scientists around the world to collaborate on the analysis, each contributing their expertise to the search for new physics.
This is all so incredibly complex, but I'm starting to get a grasp of how it all works. It's like a giant puzzle, with each piece, from the detectors to the data analysis, playing a crucial role in understanding the fundamental nature of reality.
It's a puzzle that's been billions of years in the making, and the LHC, It's giving us the tools to finally start putting the pieces together.
Okay, so we've covered a lot of ground in this first part of our deep dive into the LHC. We talked about the goals of the experiment, the different detectors, and the challenges of managing the massive amounts of data generated by the collisions. But there's still so much more to explore.
We've only just begun to scratch the surface. In the next part of our deep dive, we'll delve into the specifics of ATLS and CMS, those all-star detectives that are leading the charge in the search for new physics.
I'm ready for more. Let's see what other secrets these incredible machines have to reveal about the universe and our place within it.
All right, so let's delve deeper into these inner workings of ATLS and CMS. As we discussed, these detectors are designed like onions with multiple layers, each playing a very specific role in identifying and measuring the particles that are created in the collisions.
Yeah. And it's amazing to think about the level of precision involved. We're talking about particles that are smaller than atoms, traveling at nearly the speed of light. How do they even begin to track something so minuscule and so fleeting?
Right, that's where the innermost layer of these detectors comes in the tracker. This component uses these incredibly sensitive silicon sensors to detect the passage of charged particles. Think of it like a super high-resolution camera, capturing the trajectory of each particle as it flies away from that collision point.
So they're not actually seeing the particles themselves, but rather the tracks that they leave behind in the detector.
Exactly. And the precision of these trackers is mind-boggling. They can actually pinpoint the position of a particle to within a few microns. That's a thousandth of a millimeter. And by analyzing these tracks, scientists can determine the particle's momentum, its charge, and other crucial properties.
It's like reconstructing a high-speed car crash by analyzing the skid marks of the debris patterns.
That's a great analogy. Now, once the particles have passed through the tracker, they then encounter the next layer, the calorimeters, and these are designed to absorb the energy of the particles and to measure it precisely.
Yeah, we talked about calorimeters earlier. Can you remind me why they're so important?
Of course. So by measuring the energy deposited in each layer of the calorimeter, scientists can determine the total energy of that original particle. And this information is crucial for identifying the particle and for understanding the physics of the collision.
So it's like a cosmic scale, weighing the particles to understand their energy and impact. You also mentioned there are different types of calorimeters. What's the difference?
Yeah, so there are two main types, electromagnetic calorimeters and hadronic calorimeters. The electromagnetic calorimeters are designed to measure the energy of lighter particles, such as electrons and photons, and these interact primarily through the electromagnetic force.
Okay, and the hadronic calorimeters are for heavier particles like protons and neutrons.
Exactly. Hadrons interact primarily through the strong nuclear force, and the hadronic calorimeters are designed to absorb their energy and measure it accurately.
Yeah, it's incredible to think about the engineering involved in building these massive, intricate detectors.
Truly. The technology used in these calorimeters is astounding. For example, the ATLS calorimeter uses liquid argon, and that has to be kept at an incredibly low temperature, negative 184 degrees Celsius.
That's mind-bogglingly cold. Why do they need to keep it at such a low temperature?
Well, liquid argon at that temperature, it has excellent properties for detecting particle interactions. It allows for very precise energy measurements, and it also helps to minimize that background noise.
So to study the universe's hottest moments, we need some of the coldest technology.
Indeed. And that's not all. Let's not forget about the muon detectors. These are the outermost layer of these detectors. Muons are special particles. They're like the ghosts of the particle world, capable of passing through meters of material without interacting much.
Right. We talked about muons earlier, like the Houdinis of particle physics, escaping from the inner layers of the detector. Why are these so important?
Muons are very interesting because they are relatively stable and can travel long distances. This makes them excellent probes for studying the products of the collisions, and by tracking their paths, which are less affected by the detector material, we can glean these valuable insights into the original collision and the particles that were created.
So these detectors are really like multi-layered sieves, sifting and sorting the particles, revealing their identities and properties through a series of ingenious measurements. But with so much data being generated, how do scientists actually analyze it? You mentioned a trigger system. What's that all about?
Right, the trigger system. It's crucial for handling that enormous data flow from the LHC. Imagine trying to find a specific grain of sand on a beach. You wouldn't examine every single grain,
Oh,
right?
that would take forever. You'd need some way to narrow down the search.
Exactly. And that's what the trigger does. It acts as a super fast filter, analyzing each collision in real time and selecting only the most interesting events for further analysis.
So it's like having a team of super fast librarians who can scan millions of books per second and pick out the ones that might contain the secret code.
A perfect analogy. The trigger is designed to look for specific patterns that indicate something interesting might have happened in the collision. So, for example, it might look for events that produced a high energy particle or a specific combination of particles or events that deviate from that expected background noise.
So the trigger helps to separate the signal from the noise, reducing the amount of data that needs to be analyzed. But even after this filtering, there's still a vast amount of data left right.
You're right. That's where the worldwide LHC computing grid comes into play. It's a distributed computing network that connects thousands of computers around the world, and it allows scientists to share the data and to collaborate on the analysis.
It's like having a giant interconnected brain, with each computer acting as a single neuron, all working together to process and understand the data from the LHC.
That's a great way to visualize it. This global collaboration, it's essential for managing the sheer volume of data and for ensuring that the analysis is as thorough and rigorous as possible.
Yeah. I'm constantly amazed by the scale and complexity of this endeavor. It's truly a testament to human ingenuity and collaboration.
Absolutely. The LHC is a prime example of what we can achieve when we pool our resources and expertise to tackle, some of the most fundamental questions about the universe.
Speaking of resources, our listeners shared some source material for this deep dive, and I'm noticing some fascinating details about the detectors. One article talks about the CMS magnet, and it's so powerful that it can actually affect the Earth's magnetic field when it's turned on.
It's true. The CMS magnet is, it's a technological marvel. It's a superconducting solenoid magnet, the largest and most powerful of its kind ever built. It generates a magnetic field that's 100,000 times stronger than the Earth's magnetic field.
Wow, that's an incredibly strong magnet. Why do they need such a powerful magnet in the detector?
Well, the magnetic field is crucial for bending the paths of charged particles. By measuring how much a particle's path curves in the magnetic field, scientists can determine its momentum and its charge.
So it's like a cosmic fingerprint, revealing the unique properties of each particle.
Exactly. The magnet allows us to differentiate between particles that might otherwise look identical. It helps us to untangle that complex web of particle interactions that occur in each collision.
Another article discusses the challenges of cooling the ATLAS detector, which uses tons of liquid argon. It mentions it's like building a giant refrigerator, but one that has to withstand the radiation and vibrations from the particle collisions.
Right. It's a remarkable feat of engineering. Maintaining such a low temperature in such a harsh environment is no easy task. The cooling system is a complex network of pipes and pumps and cryostats, all working together to keep the liquid argon at its optimal temperature.
Yeah, it's incredible to think about the precision and the ingenuity involved in every aspect of these experiments.
It's truly mind-blowing. And let's not forget about, the human element here. Thousands of scientists, engineers, and technicians from all over the world have dedicated their time and expertise to make the LHC a reality. It's a global collaboration on an unprecedented scale.
It's a testament to, our shared curiosity and our desire to understand the universe around us.
Absolutely. The LHC is a symbol of human ingenuity, collaboration, and our relentless pursuit of knowledge.
Okay. We've explored the intricacies of ATLAS and CMS, these incredible detectors that are pushing the boundaries of particle physics. It's been an incredible journey so far. What's next on our agenda?
Now that we have a better understanding of how the LHC works, let's take a closer look at some of the groundbreaking discoveries that have already been made. And perhaps even more exciting, let's discuss the tantalizing possibilities that lie ahead in the future of particle physics.
We've journeyed deep into the heart of the LHC, explored its massive detectors, the incredible data challenges, and the sheer scale of this global scientific endeavor. Now let's talk about the discoveries. What groundbreaking findings have emerged from this subterranean world of particle collisions?
Well, one of the most significant discoveries, and one that captivated the world, was the confirmation of the Higgs boson back in 2012. This elusive particle, theorized decades earlier, plays this fundamental role in the universe. It gives mass to other particles.
Yeah. It's incredible to think that we can recreate conditions similar to, those moments after the Big Bang, producing particles that haven't existed naturally for billions of years. What other secrets has the LHC revealed?
Well, while we haven't found evidence for supersymmetry or extra dimensions yet, the LHC has produced a plethora of other intriguing findings. For example, the LHCb experiment, which focuses on the subtle differences between matter and antimatter. It has observed several exotic hadrons, so these are particles made up of more than 3 quarks.
Exotic hadrons. Those sound like something straight out of a science fiction novel.
They are pretty exotic. These particles, they challenge our understanding of how quarks combine to form matter. They're like rare gems, in the subatomic world, providing valuable clues about the strong force, the fundamental force that binds quarks together.
It's amazing to think that we're still discovering these new forms of matter, expanding our understanding of the universe's building blocks.
And that's the beauty of scientific exploration. Every new discovery opens up new avenues of inquiry, leading to more questions and then more possibilities. The LHC isn't just about finding answers. It's about expanding our horizons and pushing the boundaries of human knowledge.
Yeah, it's like we're explorers, you know, charting this vast, uncharted territory. And with every expedition, we uncover new wonders and mysteries.
That's a great analogy. And the journey is far from over. The LHC is constantly evolving, with upgrades planned to increase its energy and luminosity. This means more collisions, more data, and even greater potential for groundbreaking discoveries in the future.
Yeah, more power to the LHC. It's exciting to think about what the future holds for particle physics. But for our listener, who may not be a physicist, why should they care about these discoveries? What's the relevance to their everyday life?
That's a great question. While it's true that the world of particle physics, it might seem abstract and distant, it's important to remember that the discoveries made at the LHC have the potential to transform our lives in profound ways.
Can you give us 2 examples?
Absolutely. The technology developed for the LHC has already had a significant impact on other fields, such as medicine, computing, and material science. For example, the techniques used to build the LHC's powerful magnets, they've led to advancements in magnetic resonance imaging, or MRI technology. And that's used to diagnose and monitor a wide range of medical conditions.
So the technology that's helping us unlock the secrets of the universe is also improving healthcare here on Earth.
Exactly, and that's just one example. The computing power needed to process the vast amounts of data generated by the LHC has driven advancements in distributed computing and data analysis, which have applications in fields ranging from finance to climate modeling.
It's like this ripple effect. With the knowledge gained at the LHC spreading outwards, influencing and enriching other areas of science and technology.
Precisely. And let's not forget the impact on our understanding of the universe and our place within it. The LHC is helping us to answer some of the most fundamental questions humanity has ever asked. Where do we come from? What are we made of? What are the laws that govern the cosmos? These are questions that have captivated philosophers and scientists for centuries, and the LHC is giving us a new way to explore them.
Yeah, it's like we're piecing together a cosmic puzzle, and each discovery at the LHC is another piece that helps us to see the bigger picture.
And that picture is one of incredible complexity, beauty, and wonder. The universe is a vast and mysterious place, and the LHC, it's a testament to our insatiable curiosity and our desire to understand it.
As we wrap up this deep dive into the LHC, I'm struck by this sense of awe and inspiration that this endeavor evokes.
It's truly an incredible achievement, both in terms of science and engineering. The LHC is a symbol of what we can accomplish when we work together, transcending national boundaries and cultural differences in the pursuit of knowledge.
It's a reminder that science is this global endeavor, a collaborative journey that unites us in our quest to understand the universe and our place within it.
And it's a journey that's just beginning. With the LHC poised to make even more groundbreaking discoveries in the years to come, the future of particle physics is incredibly bright.
So to our listener, we encourage you to keep exploring, keep asking questions, and keep marveling at the wonders of the universe. The LHC is showing us that there are no limits to what we can achieve when we combine our curiosity, our ingenuity, and our passion for discovery.
It's been a pleasure sharing this deep dive with you. May your curiosity never fade, and may your exploration of the universe continue.
That's it for this deep dive. Until next time, keep exploring.